In this video, we're going to see how to write Lewis structures for elements, elemental ions, and simple ionic compounds. Now, let's remind ourselves of what we know. We already know how to write electron configurations for different atoms. And here I've written down the electron configurations for all of the atoms in the second period. And that's the same as saying the second row on the periodic table. All of them have got a helium core, and I can count electrons into each one. For lithium, it's second row in the S block, so this is a 2s1, 2s2 for beryllium, 2s2, 2p1 for the boron, and then every element that I go over adds an extra electron on. There's room in the p subshell. It can fit up to 6. So here are the rest of the configurations. The neon configuration I can write out like this, or it is just a neon core. I can write it like that. Alright, that's fine. But it gives me a little bit too much information. What I'm really interested in is how many electrons I've got in the valence shell. All of the action happens in the outer shell. That's where all the chemistry is. Chemical reactions are going to involve either giving or taking electrons away from the outer shell. So this is too much information. Now I can simplify this. All I really care about are the number of valence electrons. I don't care about whether they're in an S or a P, really. If I add number of valence electrons, I can count all of the electrons that are in the outermost shell. So there's 1 electron here for lithium, there's 2 for beryllium, 3, 4, 5, 6, 7, and 8 electrons in the outer shell for each of these. Now let's introduce a new notation that is going to give us the count of valence electrons without any unnecessary detail. I'm going to write down what's called a Lewis structure for each of these atoms. And what I'm going to do is write down the symbol for the atom, and then I'm going to put a dot there, and that stands for a valence electron. So there's 1 dot next to the Li. If I do the BE, I can put 2 dots around that. And it doesn't really matter where I put the dots. I could put them both together, or I could put them apart so that they're easy to count. I try to pair them up when I have to. Now when I do boron, I can draw it like this. That's fine. When I do carbon, I can do it like this. When I do nitrogen, I'm going to draw it like this. There's 5 of them. Now, notice what I'm trying to do here. I'm trying to keep the dots either north, east, south, or west of the symbol. So I don't just put them any old place. That makes it easier for me to count them at a glance. Kind of like on a 6-sided dice, they do not put the dots any old place on the sides of the dot. They group them in a consistent way to make it easier to count at a glance. So north, east, south, and west, I'm going to try and keep them there. And here I had to start doubling them up on the nitrogen. On the oxygen, I've got 6, 4. Now I'm going to start doubling them up. 5, 6, like that. Okay? On the fluorine, I've got 7. 1, 2, 3, 4, 5, 6, 7. And it doesn't really matter where I put that odd electron. I could have it anywhere. I could have done the fluorine like this. Doesn't really matter which way that odd electron points. Okay, and with neon, I've got 8. 1, 2, 3, 4, 5, 6, 7, 8. So these are the Lewis structures for for all of these atoms. And what they are is a shorthand way to represent these electron configurations. They're just showing me the count on the valence electrons, which is often all I need. Now, these things are going to want to gain or lose electrons so that they'll be like the nearest noble gas. Suppose I want to do the fluoride ion. Now, I could do it the way we had done fluoride ion before, by adding an electron onto the fluorine configuration and getting the neon configuration. I could write the electron configuration for fluoride as neon. Or I can do it like this. Fluorine has 7, and it wants 8. It wants what we call an octet. And to give it an octet, I could take an extra electron from somewhere else. Say it's that one that I wrote in a little darker there. And now I'm going to show that that whole structure has got a -1 charge. This is the Lewis structure for fluoride ion. Now, I can write a rule that guided me here in making the fluoride ion configuration. I can say the octet rule. Atoms gain or lose electrons to be like the nearest noble gas. Okay, let's put a box around that. Now, this doesn't always work for transition metals and lanthanides and actinides. It works fine for things that are in the S and the P block. We're only going to do Lewis structures for elements in the S and P blocks on the periodic table. Do you remember what the S and the P blocks were? You should. If you can do electron configurations, you have to be able to do that. The S block is the first 2 columns here, and the P block is this 6 columns here. That's the P block right there. So you have to have an element in there to be able to do a Lewis structure for it. If someone asks you, do a Lewis structure for an iron atom, the right answer is no. This really just does not work with the transition metal atoms, or with the lanthanides, or with the actinides. We're sticking only to this part of the periodic table when we're doing Lewis structures. Now, why is that useful? Because almost all of the atoms that you see in organic compounds are in the S and the P blocks. So we can write the structures for most of the organic compounds that we're going to encounter if we know just that one thing, the octet rule. Let's do a couple more ions. Suppose I have calcium, and I want to do a Lewis structure for calcium and also a Lewis structure for the calcium ion. Now, I know from previous worksheets that calcium forms a +2 ion. Now, if I do a Lewis structure for this, how many valence electrons does calcium have? Well, calcium has got an argon core. There's argon, the end of the previous row. But it's in the second column, so it forms a +2 ion. It's got 2 valence electrons that it can lose. Instead of writing out the electron configuration, I'm going to just write a calcium Lewis structure like this. And if I form a calcium +2 ion, I'm going to be taking those off. So this would be a calcium +2. Now, what I would write down for the Lewis structure is the symbol and then a +2 after it. Notice I'm using square brackets to show what I've got there. Let's do nitrogen and then an ion that forms from nitrogen. What charge on the ion do you think you're going to have? Well, it wants to be like the nearest noble gas, which is neon. So it wants to pick up 1, 2, 3 more electrons. It has 7 electrons. It wants 10. So that'll be the most common ion that forms from nitrogen. Let's do the Lewis structures for both of these. Now nitrogen has got 1, 2, 3, 4, 5 valence electrons. So I can write its Lewis structure like that. The nitride ion is going to pick up 3 more, so I'm going to write the Lewis structure down for a nitrogen atom. And now I'm going to add 3 more electrons onto it. And I did them as open circles rather than filled in dots. And now, because it has a charge, I'm going to put a -3 on the outside of that. So I put square brackets around anything with a charge and put a -3 on it. Let's do the Lewis structure for a simple ionic compound. How about NaCl? Now, NaCl is really a sodium ion hooked to a chloride ion. So to do the Lewis structure for this simple ionic compound, all I've got to do is do the Lewis structures for each of the ions and then write them down sitting next to each other. Now what's the Lewis structure for a sodium ion? A sodium atom has got 1 dot on it. And a sodium ion will be that with the dot stripped off. It's got a plus charge on it, so I'll write the Lewis structure down like that. Now how about the chlorine ion? Chlorine has got 1, 2, 3, 4, 5, 6. Whoops, let's do it down here. 1, 2, 3, 4, 5, 6, 7 dots on it. If I want to do Cl minus, I'm going to put 1 more on there. So that's what the chloride would look like. And I've covered the one that I added on a different color, but you don't have to do that. So that's what the Lewis structure for chloride ion looks like. I can write it like that with a minus on it. And just write them both sitting next to each other, and that's the Lewis structure for the ionic compound. Now let's make this a little bit easier. We've been using the octet rule to do the charges on the ions. And we've been looking at the electron configurations to figure out how many valence electrons we've got. But everything in this column has got 1 valence electron. Everything in this column has got 2 valence electrons. Everything in this column has got 3, 4, 5, 6, 7, 8 valence electrons. So if I know which column in the S and the P blocks that I am working in, I can very quickly write down Lewis structures for those atoms. Okay, let's do that. Suppose I have a selenium ion. Selenium atom looks like this. Selenium ion will be, can you tell what the charge is going to be? It wants to be like the nearest noble gas. So it'll gain 1, 2 more electrons. Let's do the Lewis structures for both of these. Now selenium is in the column with 6 valence electrons. So I can write 6 valence electrons around it. There's a selenium atom. Selenium ion, selenide ion I'd call it, has got how many electrons? It's picked up 1, 2, so it's got a krypton configuration. It's got the same number of valence electrons the krypton has, which are 8. So I can write the selenium ion Lewis structure like this. It's a selenium with 8 valence electrons around it. 2 more than I had over here. Here's a selenium atom. Here's a selenide ion. Okay? Let's do one more. Suppose I want to do the Lewis structure for a tellurium atom. Look at where tellurium is on the periodic table. It's in this column. Everything in this column has got 6 dots around it. So there it is. There's the Lewis structure for a tellurium atom. Now you'll need to, in the next video, count how many valence electrons you have around each atom in a structure.